Hi, I'm Conor Houghton, and this is lecture 11 in the information theory section of our unit Information Processing in the Brain. This lecture is about Infomax. The context here is the cocktail party problem, which we talked about in the last lecture. In the cocktail party problem, you have a number of sources in the cocktail party formulation, people speaking, and you want to separate those sources. So what you're receiving is obviously a mixture. You're hearing mixed sounds from the different sources, and you want to go back from the mixture to the original sound. In the cocktail party problem, the classic version, there's two people speaking. You've got two ears. In the classic simple version, the mixing is linear, so each ear receives a linear combination of the two signals, and you want to reverse that mixing. That's the simple version. What we would need to do in practice usually is much more complicated. For example, if you're using ICA to look at EEG signals, you have many sources and many signals. And of course, in principle, what the brain does, what the brain clearly does, is more complicated too, because we can close one ear and still do source separation. We can source separate when there's many different voices. In source separation, we're assuming the mixing is instantaneous, but of course, in the brain, we're able to separate signals even though the mixing might include reverberations and delays and so on. So this problem that we're solving, the simple version of the cocktail party problem, is a simple version, an oversimplification, but being able to solve that, of course, gives us insights into the more complicated problem. The particular algorithm that we're looking at, Infomax, well, that's interesting to us for a number of reasons. Firstly, Infomax involves ideas from information theory, which we've been studying. Also, Infomax involves ideas from neuroscience, which we're interested in, and there's a possibility that an Infomax-like algorithms might be operating, or some version of them might be implemented in the brain. We don't know. So, to recap, the idea we have here is we have the original sources. In the case that we're looking at, S will be a two-dimensional vector dealing with the two sound sources. They get mixed to form the two recordings. So, in the simple case that we have in mind, these are the sounds that arise in the two ears. But the two-dimensionality is not really important. What's important is that this is a square matrix, so we have the same number of recordings as we have sources. So we have some sources that get mixed by this 2x2 constant matrix, and then we have the recording. So this is the thing we have access to. We don't have access to this. We're kind of trying to rediscover that, and the way we do that is through an unmixing matrix W. So W is equal multiplies R to give you X, and X is supposed to be morally the same as S. By morally the same, I mean we don't necessarily expect the X1 and X2 to be in the same order. So X1 might be equivalent to S2 and S1 to X2, etc. There might be some rescaling, but basically W times M is either a diagonal matrix or a matrix with zeros on the diagonal in the 2x2 case, so it might be a permutation matrix, or it might involve a permutation as well. So we have R, we're trying to get to X. Now, we of course model these with random variables, so we have, the sources come from the random variables S1 and S2, the recordings from the random variables R1 and R2, and the thing we're trying to get, X1 and X2. So we start off with the R's, we do this multiplying by W, and we have some random variable we draw on when we look at the values of the recording, and then we have some other dependent random variables that we get from the R's by multiplying it by the W's. And these two these two X's, well, we want them to be statistically independent from each other, because we're assuming the sources are independent from each other. This is the game we're in. We have two sources. The one thing that we know about these sources is that they're supposed to be independent sources. They're not part of the same process. They're both just going on with no statistical dependence on each other. And we want to find then, well, what we receive then is a mixture. The R1 and the R2, they are statistically dependent on each other because they're mixtures of S1 and S2, both of them. The S1 part of one and the S1 part of the other means that they're not independent. X1 and X2, if we've done this right, if we've chosen the right W, they should be statistically independent as well, just like the S1 and S2. So the way that we measure statistical independence, the best way of doing it, in principle at least, is to work out the mutual information. And so the mutual information of X1 and X2 should be equal to 0 if X1 and X2 are statistically independent. So, the way it works is we have a value of W, and for a given value of W, we can go from R. The R is the thing that we can actually measure, to the x's. So once we have the x's, we can then ask, are they statistically independent? And if we worked out the mutual information, we could test that. And so the idea we have is that we want to choose the w that makes this thing true. That's the aim, that's the goal, that's what achieving source separation or solving the cocktail party problem is. It's finding the w that makes this true. Or a kind of looser version is that we want to find the w that minimizes this mutual information. And so once again, the r's that are our recordings. With a w we can then work out an x, and we want to choose the w so that if we do work out when we do work out these x's from the r's, we're minimizing as much as we can the mutual information and hopefully making it 0. Now the problem there is that the mutual information is hard to calculate. The mutual information is always hard to calculate because it requires a knowledge of the probabilities. You'll recall that the mutual information is the expected value of the log of the joint probability divided by the multiple of the marginalized probabilities. It's minus that. So no, it's not. It's plus that. So to work out the mutual information, we need the probabilities, and the probabilities are hard to estimate, particularly for continuous random variable. And so what we're going to do instead is we're going to use this formula, which we actually originally used, the definition of the mutual information. It says the mutual information of x1 and x2 is equal to the entropy of x1 plus the entropy of x2 minus the joint entropy. And what we're going to do is we're going to, instead of minimizing this, we're going to maximize that. Now you might say that's crazy because you've got the h of x1 and the h of x2 here as well. So if we're busy maximizing that, well, maybe we're making these bigger as well, and so we won't be making this any smaller. In fact, x1 and x2 are both kind of mixtures of S1 and S2, no matter what your W's and your M's are, no matter whether x1 and x2 are independent or not, they're both mixtures of the original S's. And so you expect that these things have entries that don't change very much as W changes. And so the amount of information in x1 will be roughly the same no matter what mixture of R1 and R2 X is composed of. The same for X2. On the other hand, the joint entropy, well, that'll be very different. If the X1 and X2 are giving you the same linear combination of R1 and R2, then the joint entropy will be just equal to one of the two individual entropies. Whereas if they're doing something completely different, then the joint entropy will be the same as the sum of the two entropies. And so this is the thing that you expect to vary a lot with W, and that's one of the assumptions that's been made. Now, what we're going to be doing then is instead of minimizing this, we're going to maximize that. And that's where the name for the algorithm comes from, because obviously this is the information in x1 and x2, and we're trying to maximize that information, so it's called Infomax. I should say that this algorithm was discovered 25 years ago by Bell and Sinowski, both obviously genius level people, because this is a genius level algorithm in the sense that you have to make a number of different steps that are not at all obvious, at least to me. And so they must have had some tremendous intuition, because it doesn't seem like you're going in the right direction here. We have something that's hard to calculate. We say, well, this is hard to calculate. Let's calculate this instead, or do something that involves calculating this instead. And it's not at all obvious that this is any easier to calculate. So, here we go. We're trying to maximize this Shannon's entropy. It means we're ignoring these two terms. That's probably okay. We can see that now. And it means that we have some faith that this is going to somehow be easier to calculate than this. And that's not at all obvious to me. So this is one of the points in developing the algorithm where you come to a problem that the solution's not straightforwardly clear, but somehow Bell and Sinowski were able to push forward, and they felt that they had some intuition which said that this was something that you could do, and in the end it would all work out, as indeed it does. So they're assuming that h of x1 and x2 is easier to calculate than the mutual information. In fact, that's not at all what happens. H of x1, x2 isn't ever calculated. But we're not actually trying to calculate h of x1, x2. We're trying to calculate the value of w that minimizes it. And it turns out that if you're doing gradient descent, in other words, you are doing a hill climbing algorithm to try and maximize this h. I said minimize a second ago. I meant maximize this. We're trying to maximize h. We're just trying to go up the hill, which means knowing the gradients, the derivatives. In which case, it turns out we don't ever have to calculate h, we just have to calculate the derivative of h with respect to w. And what we'll find out at the end is that that's something that we can do, or at least the bit that we need to do of that is something that we can do. So there is obviously a big problem with what I just said, which is that we're trying to maximize the entropy. And the differential entropy, and the one thing we learned about the differential entropy over the last few lectures is that it doesn't behave very nicely when you start scaling things. Now this is the joint differential entropy. We only ever did the one-dimensional case before. But you can imagine, and you can check with a quick calculation, that things don't get any better with the joint entropy. If you scale the x1, well, you get this extra log term coming out the end, and the same thing is true if you scale the x2. And if you scale them both together, of course, you get a lambda squared term coming out the end, which gives you a 2 log of lambda. And so, if you're trying to maximize h, obviously the way you can maximize h is by multiplying x1 and or x2 by lambda. If you make them bigger, then the h gets bigger because this log term gets bigger. And so you're able to, if all you were trying to do was maximize the h, you could change the h, or you could choose w's, which basically scaled x1 and x2 in such a way that you would make h bigger without telling you anything about mixing and unmixing. So it was sort of a useless way of solving the problem of making h big. Of course, this log term here in the mutual information will cancel because of the hx1 and the hx2. So it doesn't really tell you, or precisely doesn't tell you anything about the mutual information as well. This is one of the ways that you can change h without changing the mutual information. So what do we do? Well, Bell-Slansky's idea was to use the behavior of neurons. When you have a neuron, they often appear to have some sort of saturating behavior. If you push more current into a neuron, it spikes faster. But if you keep going with that, after a while, it'll stop getting any faster. It kind of levels out. It saturates. And so you can think of, it's a common in computer science simplification to think of neurons as implementing a saturating nonlinearity, something like this thing here. So what we're going to do is we're going to, instead of thinking about the x1 and x2, the thing that we really want to deal with, the output variables, we're going to deal with y1 and y2, which is what you get if you run x1 and x2 through a saturating nonlinearity. So this is an example of saturating nonlinearity. Excuse me. No matter the value of for values of u going from minus infinity to infinity, g will always be between 0 and 1. And I have a picture of what g looks like here. So this is g. This is an example of g. There's other g's you could use. And as you could see, for u very small, g is more or less pretty close to 0. For u very large, g is pretty much close to 1. And in between, has this almost linear behavior, or approximately linear, close to being linear, near u equals 0. So that's the saturating nonlinearity. What you can imagine now is if you're running a probability distribution through this saturating nonlinearity, if the probability distribution is too wide, then a lot of the time will be spent, the distribution of u will give you lots of values near 0 and lots of values near 1 and fewer values in between, and that won't be very entropic because a lot of the probability mass will be clustered in the 0 area and the 1 area. So if you've got your distribution before you go, the distribution for u before you go through the nonlinearity, if that's around here, well then running through the nonlinearity won't make much difference. But if the distribution is very wide, then after you run through the nonlinearity, you'll get your distribution for g rather than for u will have a lot of stuff at the 0 and the 1. So I have an example of that. Let's imagine that x is uniform. So we're just dealing with the one-dimensional case here. X is uniform, and I've made the uniform range go from minus a over 2 to a over 2, and so the height is 1 over a, so the integral is 1. So that's a uniform distribution. And now I'm going to calculate, so that's px of x. Now I'm going to calculate the corresponding pg of g. So we know how to do that. We worked that out in the last lecture. It's the original probability density, but you've translated from g to x before getting p of x, and then you have the dg dx here, which is this Jacobian factor, this rescaling factor. So if you run the uniform distribution and you use that, that's your p of x. Now I work out p of g, where g is g is equal to g of x, this nonlinearity here. So the x goes where the u is. Then these are the distributions you get. So for a equals 1, well, that's the case where the input stays very much near the middle of the distribution, so it doesn't actually change it very much. It rescales a bit. That's all. So that's here, and it translates it a bit as well. The a equals, and you can see it's actually very close to being also a uniform distribution. For a equals to 5, it has a little bit of a bend up at the end, but it does spread it out a lot more. And we know the differential entropy likes being spread out. That increases the entropy. So by increasing the range a bit over more of the interval from 0 to 1, then you're going to have increased the entropy probably. Whereas here, you can see that for a equals 10, you're getting spikes at each end, and so very much the probability mass is being concentrated at these two ends here, which means that the entropy is likely to be lower here, because it's fairly predictable that the result will either be around here or around here. And in fact, if you work these out, this is the case. So for the a equals 1 case, you get minus 1.41. For the a equals 5 case, the entropy now is actually bigger. Again, it is more spread out. For the a equals to 10 case, though, the entropy is now falling again. You can see I didn't plot a equals 15 because in fact these spikes are very high. If you go there, the entropy gets even smaller still. Okay, so that's the idea behind this saturating and nonlinearity. It is actually suits distributions whose width kind of matches the range of the nonlinearity. So this range of nonlinearity, it likes things that go from -5 to 5, and so the distributions that have that kind of a width will be favored by this nonlinearity. Anything that's wider or narrower is likely to have a smaller entropy. And of course, the in the case that we're looking at, we're adding this w to make, that's basically to put the nonlinearity in the right place. This x will be w, some combinations of R1 and R2, and so that will provide the scaling. And so the scaling that's chosen, and we'll see this later on, should give you a distribution that matches the saturating nonlinearity. Okay, so this is now our plot. We had the original s's, we mix them, so we don't have the s's, but the s's are there. They get mixed, and we have the r's. We want to unmix them, but we're first of all going to run them through this nonlinearity. So I'm using this dot notation here. The g dot is like you get the scalar function and you apply it to each of the components of this vector here, the vector you get by adding the x to the w. And so what we're going to try and do is we're going to try and minimize the h of y here. And you imagine h of y is going to be minimum if the g of x, the g1 and g2, or y1 and y2 are statistically, this entropy is going to be maximum if y1 and y2 are statistically independent, and if the x plus w, if the x and the size of the x, the range of the x, and the position of the x given by this translation w, provided they center the distributions in the middle of this saturating nonlinearity. In other words, just by making x have a wider range, eventually it's going to start going beyond the range of the saturating nonlinearities. You get these spikes at the end, which will decrease the entropy. Okay, so what we're trying to do now, or the plot, is we're going to maximize h of y, and as I said, h of y1 comma y2. By maximizing h of y1 comma y2, we are going to be choosing w's, big w's, so that y1 and y2 are independent, and and this is kind of less necessary for our basic goal, we're going to be choosing them so that it's not too big and not too small, so it fits nicely into this saturating nonlinearity. And this is just a piece of notation. So for later convenience, so G is the thing that goes from X to Y. We have F will be the notation as the thing that goes from R to Y. So in other words, what you do, what F does, and F is, as you'll see, a vector, it takes R1 and R2 and multiplies them by W. It adds the W vector. So in other words, F goes from here to here by first of all getting X equals W times R, then adding the W to it, and then putting it through the saturating nonlinearity. So this problem is actually quite a tricky problem to do maths. We didn't do very much practice with differential entropy, certainly not when there was with joint entropies. So I'm going to deal with the one-dimensional problem first, show that it's solvable, and then just appeal to common sense to say that the two-dimensional example is solvable in a similar way. So the one-dimensional problem, the curious thing is that it doesn't actually achieve anything, because what it's going to do is going to choose the big W and the little w to maximize this y. But here x is x is just a multiple of r. We're not there's no s here. We're not solving any problem. We're saying we have some random variable r. Those values are little r. We're multiplying it by w. We're running it through the saturating nonlinearity, and we want to find the choices of this big W, which is now a scalar, obviously, because R is one-dimensional, and this little w that makes the entropy of this y as big as possible. So one way of thinking about that is that we're trying to maximize the information that y has about R, and this mutual information here, the information that y has about R, is equal to the entropy of y minus the conditional entropy of y given R. And the conditional entropy of y given R, well, you'd think that this would be 0, because y is determined by R. So if you know R, you know y, just because y is calculated from R by just this set of functions, multiplying it by w, adding the little w, and running it through the saturating nonlinearity. And so certainly in the discrete case, this would be 0. Unfortunately, it's not quite that simple here. In fact, in this case here, this is going to be minus infinity, because it's a differential entropy, and as you remember, the differential entropies don't have such nice properties. For example, they're not bounded below by 0. But it's not really going to matter, because it is actually a constant, and we're only ever going to deal with derivatives. So this value here is we'll just regard it as a constant. What we'll think is that by maximizing this, we'll also be maximizing that. So how do we maximize h of y? Well, h of y is equal to minus the integral of p of y log p of y dy, and this is estimated by this h tilde of y here, which is just one of these. Why is that? Well, this here is the expected value of log p of y. So if you have lots of these h tilde of y's, in other words, so yt here is supposed to be one of the values of y. So you draw from the recording, you work out what y is, that gives you a value. If you have lots of those values and you take the statistical mean, well, that should approach this h of y, precisely because this h of y is the expected value of the log of p of y. And so as you get lots of sample points, this thing approaches that thing. So we need to work out this h of y, and the problem is that the estimator still has the probability in it. And so you might worry that working out the estimator is still difficult because we know this p of y. But the thing to remember is that we're not actually interested in finding out the actual value of h of y. We're interested in the w, the big W and the little w, what will be in the two-dimensional case the unmixing matrix, and then the little w is this translation that we need as part of the machinery of using the saturating nonlinearity. And so we don't need h of y, we just need the derivative of h of y, because we're going to do gradient descent. So this is the usual thing, that if you're going up a mountain and you want to know what way to go up the mountain, but you can only see around you locally, then the thing you need to know is which way is up. What's the gradient of the mountain? What's the derivative of the height of the land relative to the moving in the x direction or the y direction? Knowing those two derivatives gives you the gradient, d height dx, comma d height dy, and that's the direction you go in. Or you might have other strategies. So that's the direct descent approach to hill climbing. In fact, from a numerical point of view, it's sometimes better to zigzag up to avoid getting caught into pathological oscillations as you go through narrow valleys and so on. So that's conjugate gradients. So we might necessarily go directly up the gradient, but from a numerical point of view, if we want to find the maximum of some objective function, in this case h of big Y, then knowing the gradient is a good start, and that's what we're going to do here. So we don't actually need h of y, we just need its gradient. So how do we do that? Well, we know that this are following the same calculation that we saw in the last lecture, based on our knowledge of the transformation properties of a gradient, the fact that p of y is a gradient. We know this estimator here is equal to the estimator h tilde of r plus the log of this f prime. So that again is the same, it's basically coming from the log of this. It's the same transformation law, or the same relationship between entropies that we had before. So the entropy, again, that we're interested in is equal to this entropy, which we don't know either, the entropy of the underlying recording, plus the log of f prime, where f prime is the function that brings you from r all the way over to y. But the interesting thing is that this here, we don't know the value of this. I mean, you could try estimating it by taking the recording lots of times, trying to come up with some estimate of the probability of the different values of the recording. But this thing here is does not depend on the parameters. And so when we take the derivative of this, this will just give 0, and all we need is the derivative of the f prime. And that we can do. So what we need is dh dw and dh d little w, and we know g of u, the saturating nonlinearity. By actually taking the derivative of that, we can see that the dg du is given by g 1 minus g. So that's just a question of differentiation. And so if we put all of that together, it's actually possible to work out the log of f prime. So f prime, well, f was all the way back here. F is the thing that brings you from so f of r is the thing that you multiply r by w to get x, you add w, you run it through the saturating nonlinearity, and that gives you f. And so given that we know the derivatives of the g, the derivative of g, we can work out f prime from the chain rule, and this is what you get. Okay, and you can see that here. You get the w from the fact that you have a w times r, and you get the f and the 1 minus f coming from here. And so then we get, so that gives us this derivative. We can push this back into the definition of h tilde of y, and we run it all the way through, and we end up with a formula from here to here. And so this is just a matter of algebra, which you can go through yourself. We get a formula for the derivative of h tilde of y with respect to w. And we can do the same thing, it's actually a slightly easier calculation, for h tilde with respect to the little w. So, given all of that, we now have what we need, the gradient of the objective function, in terms of stuff we know. So r, we know that's the thing that we draw from the sample. If we have for a given value of big W and little w, you can work out y. And so for a given value of little w and big W, in other words, for a particular position on the side of the hill, we can work out which way is uphill. given by these gradients here. And so the miracle is, and this really is, I think, amazing, is that we've found explicit formula for the gradient in terms of the data and in terms of the parameters. And so we can use whatever hill climbing algorithm we like to now ascend the hill. And as I said before, steepest ascent, you go straight up the gradient. Conjugate gradient, you kind of zigzag up the gradient. Metric gradient takes into account somehow what you mean by a big step and a small step in different directions. And it turns out metric gradient works particularly well for this Infomax algorithm. A sort of supplementary version of the Infomax argument due to Amari uses metric gradient descent, and everything works out very nicely. So let's have a look at how this would work in this one-dimensional case. So we have some here, I've just drawn some original distribution, PR of R, and then if you do the gradient descent, you end up with particular values of W and W that make it look a bit like this. So this is what you would get if you started off with this P of R, you ran the algorithm, you'd end up with this distribution here. So this is the distribution for U of WR plus little w. And then if you shove that through the saturating nonlinearity, you actually end up with something like this. You end up with something that looks an awful lot like a uniform distribution from 0 to 1. And so the effect of the saturating nonlinearity is, well, the effect of the Infomax on this distribution here is to scale and move the distribution so that when you put it through the saturating nonlinearity, it comes out as being almost a uniform distribution. And so that's its way of maximizing the entropy. Now back to the two-dimensional case. I didn't do the two-dimensional case, but the calculations turn out to be more or less the same. It's just the complication is that you're dealing with these y's here now should be vectors, and you're you're dealing with two-dimensional objects, and so you have your w's, instead of just being scalars, are now matrices. But the calculations actually turn out to be more or less the same. If you go through it carefully, you discover again an explicit formula for the gradient of the objective function. And so if you use this to hill climb on the objective function, you can end up well. That gives you a way of finding the W matrix that performs the unmixing, and this is the Infomax algorithm. Thank you.